Hello students, my name is Shashank Shekhar and today is the second lecture of the chapter Aldehyde Ketone and Carboxylic Acid. So yesterday we have started with the nomenclature of this aldehyde ketone. Today we will see the preparation of aldehyde and ketone. We will see some of the mechanisms also. Tomorrow we will see most of them. Today basically we will be seeing the common reactions like our oxidation, means the preparation of your aldehyde and ketone, you're doing oxidation and all of those. We will see only one type of specific reaction, that is Rosenmund reaction. Okay. Tomorrow we'll see all of the remaining one. So let us start our today's class. As I have told in the previous class that we will be looking at the reactivity of the carboxylic acid using the structure of the carbonyl structure, the structure of the carbonyl atom. We will continue that thing after covering this preparation part. Okay, so we will continue that thing. But for now, let us go with the our flow. So we have seen the nomenclature. We have discussed something about the nature of the carbonyl group. We have not related it with this reactivity, but still we have discussed what is the bond, what does this bond looks like. Okay, further we will move to methods of preparation. We will see half of them today. So today the most of the common ones will be covered. So the common ones like our oxidation of your, say we take an alcohol and oxidize it using a oxidizing agent, or we take 1 degree to produce this say aldehyde, 2 degree to produce this ketone. What are the reaction conditions? All of those we will see today. Clear? Regarding some specific reaction, name reactions, we have only Rosenmund for today. We will see Stefan reaction, Itard reaction, all of those in the next lecture. Okay. And coming back to the chemical properties, which I have told you that I will cover in the next class, that will be covered in the next class. Okay, that is in the 4th lecture. So if you look at the syllabus here, the topics of this today's lecture, first we will see that this dehydrogenation of alcohol. You must have seen this reaction in the alcohol chapter also, but all this, since it is related directly to the preparation of aldehyde ketones and carboxylic acid, so I will teach this today also. Further we will move to oxidation of alcohol, how this oxidation done with the help of PCC first of all. Then how can we convert the secondary alcohol into ketone. Further, we will move to some previous reactions of class 11, that is ozonolysis of alkene, which gives us ketone or aldehyde depending upon the nature of the alkene, and then the hydration of alkynes. Okay. And as I have told that we will see some reactions, so we will see the Rosenmund reaction today. It is basically a type of reduction. How is it a reduction? So we'll see that. We'll see to that. Clear? Now, first of all, dehydrogenation of alcohol. So here you can see that we have 3 types of alcohol here. First one is 1 degree alcohol, then we have 2 degree alcohol, then we have 3 degree alcohol. So if we use the 1 degree alcohol in the presence of copper, so here I put up a schematic diagram of the setup that is being used to do the metal oxidation of this alcohol. So what it is, how it is looking like. So you can see that we have a copper surface here which allows the settlement of this alcohol group. Further, it is supported on this CuZnAl2O4. So this is basically for your electron extraction. So you know it very well that what is oxidation. So we are seeing that here the oxidation is occurring. So that would involve something which can take up the electrons so that it can be oxidized. And you know that this Al, this complex that is containing Al, is a type of Lewis acid, and it will also accept electrons from this group. Clear? Okay. So what are the specification of the reactions? Okay, so one more thing, you do not have to worry about this complex or this complex. Just focus on this reaction condition, that is 573 Kelvin and your copper metal. So what do? We take an alcohol, that is the primary alcohol, because this carbon is attached to only one alkyl chain, and we do the dehydrogenation of alcohol using copper. So since it is a 1 degree alcohol, so it will give aldehyde because the carbonyl group will be added at the extreme center. And I have told you in the previous class that if the carbonyl group is at the extreme center, then it is a chance that it would be an aldehyde, not a ketone. Yeah, it can be carboxylic acid also, but that is a different case. So today we are only focusing on this aldehyde and ketone. So therefore it will give aldehyde. Further, if you have 2 degree alcohol, say we have 2 degree alcohol, then in that case we will get ketone, because In ketone, the carboxylic group is present between two carbons. Further, what happens if you take 3-degree alcohol? So in case of 3-degree alcohol, simple removal of H2O takes place to give alkene. To mention here, there is the temperature. Okay, so the temperature is kept very high so that this reaction can be facilitated. Clear? Okay, so we are done with this dehydrogenation. So in a nutshell, I would say that if we have a 1-degree alcohol, so if we take copper metal supported on an alloy, then at 573 Kelvin it would give aldehyde. Similarly, if we take secondary alcohol and heat it with copper at 573 Kelvin, then it would give ketone. Further, if we have a 3-degree alcohol, then it would give this alkene. All of these three reactions are kind of oxidation reaction only, because in all of these reactions we are removing hydrogen, and removal of hydrogen is purely oxidation. Okay, now we will move to the general oxidation of alcohol. The general, I means we take a reagent, unoxidize it. So if you see that the structure of alcohol, two types of bond can be broken. So we have discussed this in the alcohol chapter also. We will discuss it now also. So if you see here, there is two types of bond that can be broken. First is the bond between O and H, and second is the bond between C and H. Okay, so two types of bond can be broken to give this carbonyl. So if you see this, compare this and this, you can see that this hydrogen has been taken apart, plus this hydrogen has been taken apart, and we have seen a double bond between carbon and oxygen. Clear? So this is basically the oxidation of alcohol, in which the formation of carbony oxygen double bond with cleavage of OH bond and COH-CH bond takes place. So this is, the product form is called oxidized product. Clear? Now this reaction are also known as dehydrogenation, because we are removing two hydrogens from here, plus we are just making bond between carbon and oxygen, double bond between carbon and oxygen. Now we can do it in two ways, basically in two steps. So first of all, we can remove one of the hydrogen from this side and one of the hydrogen from this side to give an aldehyde. Now we can add one oxygen to give carboxylic acid. So these both reactions are of course oxidation only. So this is our oxidized product. We use a milder oxidizing agent. Now what we do, we take a stronger oxidizing agent. So it will convert this oxidized product into a much more oxidized product, that is carboxylic acid. Okay, so in this preparation, since we are preparing our aldehyde, so we will look up to this part. We will also look to this part in the carboxylic acid topic. But for now, since we are focusing on the preparation of aldehyde and ketone, we need such kind of reactions which will oxidize this primary alcohol into aldehyde. Clear? Okay, now let us start with a weak oxidizing agent. So I have told you earlier that if you take a primary alcohol, then it will be converted into aldehyde and not ketone, because that would require a second alkyl group on the right side, on the left side where the hydrogen is present, and that is not done in oxidation. So for that we take this PCC. It is called as pyridinium chlorochromate. Why is it called so? So here is the structure of pyridinium chlorochromate. This base is called as pyridine and this is called as chromate. Okay, this is called as chromate. So its structure looks like this. Okay, so it is drawn here. So if it is not clear, let me demonstrate it for you. So we have a chromium here which is attached to three oxygens. With one it has a double bond and the rest of two has single bond. Now the one which has the single bond O is further attached to two hydrogens to complete its octet. So this is the chromate, and we have the pyridine. So why it is called pyridinium chloro? Because we have a chlorine counter atom also. So what it does is that this pyridine abstract a base from here. Okay, and pyridine looks like this. Basically pyridine looks like this. So when it take a base, when it takes an acid H plus, then it converted into pyridinium. Clear? So there are two types of again alcohol possible. First is 1 degree and second is 2 degree. Okay, one more thing. We can also have 3 degree say this alcohol. So what will happen in that case? For that we have to take a much more strong oxidizing agent, and in that case it will be converted into carboxylic acid. Okay, so we'll see the example of those in the carboxylic acid topic. But for now, let us focus on PCC. So we have taken two types of alcohol. This is the 1 degree alcohol. This is the 2 degree alcohol. So if we take 1 degree alcohol, then it is converted into aldehyde. Very clear. And if you take 2 degree alcohol, then it is converted into ketone. The reagent is the same. Okay. And the reaction goes through a concerted mechanism. So we'll see the mechanism of this, not of this, of the other one, because this goes through a concerted mechanism and it is difficult to follow. So I would suggest you to just remember the functioning of this reagent, that it converts your primary alcohol into aldehyde and secondary alcohol into ketone. Also, say we have a allylic alcohol, which looks like this. So I'm just giving a new reagent for you. So I think it would be important. It can be asked in the exam. So if we take selenium oxide, SeO2, okay, if we take selenium oxide, then it will be converted into your alpha beta unsaturated ketone. Okay, alpha beta unsaturated ketone or conjugated ketone. Clear? So for that we take SeO2 and reflux it. So if you take allylic alcohol, what I am saying is that, suppose we took allylic alcohol like this. Allylic means this carbon that is attached to your alcohol is attached to adjacent carbon, which is sp2 hybridized. So if we treat it with SeO2 and reflux it. So reflux is basically a chemical procedure. It is a laboratory procedure in which we constantly treat it with the reagent. Okay, so it is a type of, you can say, we are treating it again and again. I cannot say put it in words, but think it as a harsh condition. Okay, so we are applying this SO2 under harsh condition, that is reflux. So we will get this thing. Now, so one should ask that why are we taking SeO2? Why can't we take this PCC when we have double bond? So listen, students, there is a possibility that reaction is happen, and the NCERT has given one reaction also, but in some cases this double bond is not appropriate, okay, for the reaction to take place smoothly. So therefore, a much better oxidizing agent is used, that is SeO2, selenium oxide. Clear? So this is our thing. Now we are done with this PCC. Let us move to secondary alcohol. So the previous one we were using this primary alcohol. We also use secondary alcohol to convert it to ketone. So if we have a secondary alcohol, then we do not have to worry. We can take Jones reagent. It is a very strong oxidizing agent, which is basically, this is your Jones reagent, that is chromic acid. So if you take such strong oxidizing agent in case of your primary alcohol, then it would not be converted into aldehyde. Instead, it would be further oxidized into your carboxylic acid. So we cannot use it against primary alcohols if you want a less oxidized product. But if you take a ketone, for it to convert it into carboxylic acid, CC bond has to be broken, and that requires very harsh condition. It cannot be done under this weak reducing agent. Therefore, we can use this thing to convert our secondary alcohol into ketone, or we can use KMnO4 also. So it converts your secondary alcohol to ketone. So the same thing written here, that it cannot be used to convert your primary alcohol to aldehyde, as it would be further oxidized to your carboxylic acid. Okay, so you may be asking that, okay sir, why do not we isolate it while it is just converted into aldehyde? So it is very difficult to do so, because this occurs in a very short span of time. As soon as it is converted into aldehyde, it quickly gets converted into carboxylic acid, and it is very difficult to isolate this aldehyde from the solution. Now let us look at the mechanism of how this Jones reagent works. So here is our Jones reagent. We have alcohol has oxygen in it, and oxygen has lone pair, and this chromium has empty d orbital. So first of all, this oxygen will donate its lone pair into chromium d orbital. This will move the double bond between chromium and oxygen onto oxygen, and this kind of adduct will be formed. Clear? Now since we have water in this, Since we have water in this, it will take your H from here and will create this kind of thing. And plus, when this oxygen, say it is a kind of E1CB elimination. It is a type of E1CB elimination. Now I will not say elimination. It is a kind of substitution. So here the oxygen of the alcohol is attacking your chromium and it is kicking out your OH. Clear? Now in the next step, what happens? This H2O takes one H and we are left with this. See this ketone. So these bonds move here and this is kicked out. And we got this chromous acid plus H2O. So this is the reaction mechanism for Jones reagent. You can be also given this kind of thing, K2R2CO7 H plus or Na2Cr2O7. So all of these are strong oxidizing agent, or KMnO4 also, it is mentioned here also KMnO4. Okay, so if you use any of these oxidizing agent and if you have a primary alcohol, then it will be directly converted to your carboxylic acid. But if you have a secondary alcohol, then it will be converted into ketone and it will not be further oxidized. Clear? So this is the secondary alcohol treatment with your oxidizing agent. Next, we will move to ozonolysis. Now, ozonolysis reaction may look simple at first sight, but it is quite a difficult reaction to follow because of the later on products. What is later on products here? Suppose you have done the ozonolysis. Okay. So, what does ozonolysis do? This double bond react with this ozone. So basically what happens is that this double bond attack on this oxygen, this moves here and this attacks on this carbon. So all of these steps occur in a single step. Okay, so how does it looks like? You have a double bond here of the alkene, then you have your ozone. First this negative charge will attack here, then it will go here and it will move here. Suppose it is attached to some alkene, say. So at last you will get this kind of intermediate. You will get this kind of intermediate. So it is shown here also. Okay. So next what happens? So this one is not the final one. So we got this one from this only. So this is converted into this. How? So let me draw it for you. Okay. We have this. Sorry. So let me show you how does this mechanism goes. So we have alkene here, okay, and we have ozone, which looks like this. This is our ozone, okay. Now, sorry for the mistake. So it will be here. So it will attack here. This will move here, and this will be neutralized. We'll get this type of structure. Now what will happen? This will be pushed, okay, and you will get this kind of structure. This will go on this oxygen. Will create a negative charge on this oxygen, and here we'll get a positive charge plus this thing. Okay. Now what will happen? Now in the next attack, what will happen is that this thing will be inverted. So let me write it invertedly for you. Okay, this thing will be inverted, and this lone pair, it has a positive charge here, it has a negative charge here. So it will attack here. Okay, it will attack here. This will attack here and this will go here. So it will result in, this will go on this oxygen. Okay, so this will result in, if you follow this thing, you will get this kind of structure. Okay, now after forming this, depending upon the nature of your, say, workup, it will just cleave this bond accordingly. So since once we get this, okay, so depending upon the workup, so if we use this dimethyl sulfide, that is DMS, it looks like this, CH3 on both sides, or zinc plus acid. So these both are reactive workup. So in that case, you will get your ketone and aldehyde. Okay. Now further, if we use oxidative workup like H2O2, then it will give your ketone plus carboxylic acid. So if you see here, it is basically an electrophilic attack of this ozone on this alkene. So alkene is acting here as a nucleophile. Okay. Now generalization of alkynes give carboxylic acid. How it happens, we will see in the carboxylic acid preparation. But just for now, assume that okay, upon the workup, depending upon the workup, if you have reductive workup like your dimethyl sulfide or zinc plus acid, you will give your ketone plus aldehyde, and if in case of your oxidative workup, that is H2O2, it will give your ketone and carboxylic acid. Clear? So this is the ozonolysis of alkene. Now we will move to hydration of alkynes. You must have studied this reaction earlier also. If not, no problem. So what we do, we take an alkyne. What we take? We take an alkyne and we do the addition of water in presence of either H2SO4 or HgSO4. Now both this H2SO4 and HgSO4 have a electrophilic nature. So it can act as an electrophile for both for alkynes. For both of these can act as an electrophile for alkynes. So what will happen? Say we take an example of Hg2 plus. So this Hg2 plus will form an intermediate which would look like this. So basically it will form bond with this pi bond of the, say, alkyne and form this kind of intermediate. Okay. Next what will happen? Our H2O will attack and we will result in this thing. Now in the next step, this will undergo ketone enol tautomerism to give our required product, and further hydrolysis of this will give us your final ketone. Clear? Okay. So it is happening in this way. So we can take your H2SO4 also. For that case, it would be forming a complex that would look like this. Okay, it will look like this. So why I am giving this dots here? So because it is not a complete bond, basically interaction has been set up because hydrogen cannot form more than one bond. Okay, so at the same time this breaking and making a bond and further attack of this H2O or hydrolysis using H2O, we get this ketone. Clear? So this is the next method. Now we will move to some preparation of your aldehyde, which are specific reactions. So what are the specific reaction we can use? First is the use of acid chloride or acyl chloride. So for to students, one more thing here. So in the next class, we will see one more slide that would be covering our, when we will see this carboxylic acid, we will see what this acyl chloride, this amide looks like. Okay, so this is very important to remember all of this structure or substrate. These are very important because in the exam time, you can be facing difficulty to deal with this substrate names. It would be directly written in the exam that since take we have acyl chloride and it react with these to give these, and in that case you will face difficulty because you do not know what this acyl chloride looks like or your amide look like or your imine looks like. So you should at least be aware about the general structure of each of these. Okay, so since we are taking acyl chloride, so it looks like this. Basically it is a derivative of your carboxylic acid. So since I have not started carboxylic acid, I have not covered this part, but definitely when we will see this carboxylic acid, we will see the derivative of the for the same. Further, We can also use nitriles and esters. So in case of nitriles and esters, we take this, say, Grignard reagent, or we can do the Stephan reaction, and using all of those we can create our aldehyde or ketone. So what will happen if we take hydrocarbon? So if suppose we are taking a methyl benzene, so if we take methyl benzene, you can use chromyl chloride or other formic acid. If not, we can also use side chain chlorination followed by hydrolysis, that would give you aldehyde. Then by Gattermann-Koch reaction. So we can use each of these reactions to get our aldehyde. Clear? Some of these are for benzaldehyde, benzene is attached to your aldehyde. Some of these for aliphatic aldehyde, but this all are specific reaction and are performed under specific condition. Okay, clear? Now let us move to this first reaction, that is Rosenmund. Today we will see this Rosenmund only. Tomorrow we will see the left part. Clear? Now next is our Rosenmund reaction. So this Rosenmund reaction mechanism is not so popular or is not taught, but I am giving you an overview because students are being curious about the this reaction mechanism, that how this reaction happens, and I think it is a very good practice to keep a track of all of these. I would say that you should not try to remember each of these, but at least just keep a track of those so that you can build up an idea if a new reaction is given to you. Okay, so for that reason I would suggest that you should be seeing at the mechanism, do not try to remember it, try to get through the product directly. But I would suggest you, just if you are at the starting phase of your preparations, then you should be looking at the mechanisms too. Okay, so we are just with this Rosenmund reaction. So what we do take for this Rosenmund reaction, we take a acyl chloride and we hydrogenate it over catalyst palladium on barium sulfate. So this reaction happens like this. So this barium sulfate is basically present to poison the reaction. I will not go very deep into it. I'm just giving you a small statement that this barium sulfate is there to poison the reaction. The most of the role is played by your palladium and your hydrogen. So first of all, the metal insertion takes place. Okay, this metal insertion takes place how? The bond between carbon and chlorine is broken and one palladium is inserted in between. Okay, first of all this happens. Then what will happen? We have hydrogen. This hydrogen will attack. There will be a nucleophilic attack on this center because we have this palladium. It has increased the nucleophilicity of this carbon because it is very much electropositive in nature. Clear? Therefore, this hydrogen will donate one hydride ion and one H plus will be taken up by the Cl. And at last we'll get HCl, our palladium back, and an aldehyde. Okay, so the overall reaction looks like this. We have an acyl chloride. We treat with H2 PD BaSO4, where H2 is our reagent, PD is our catalyst, BaSO4 is our poison. It basically stops the reaction from proceeding further. Okay, so this thing gives us benzaldehyde. Okay, so it basically involves metal insertion and nucleophilic attack of hydride. Clear? So this is one of the Rosenmund reaction. So as I have told you earlier, we will encounter more and more name reactions in the next class. But for now, let us keep it to this Rosenmund today. Okay. So with this, I would end my lecture.